So today we will be doing the lost cow problem in the Usaco bronze complete search section. Farmer John has lost his prize cow Bessie and he needs to find her. Fortunately, there is only one long path running across the farm, and Farmer John knows that Bessie has to be at some location on this path. If we think of the path as a number line, then Farmer John is currently at position X and Bessie is currently at position Y, unknown to Farmer John. If Farmer John only knew where Bessie was located, he could walk directly to her, traveling a distance of X minus Y. Unfortunately, it is dark outside and Farmer John can't see anything. The only way he can find Bessie is to walk back and forth until he eventually reaches her position. Trying to figure out the best strategy for walking back and forth in his search, Farmer John consults the computer science research literature and is somewhat amused to find that this exact problem has not only been studied by computer scientists in the past, but that is actually called the lost cow problem. The recommended solution for Farmer John to find Bessie is to move to position X plus 1, then reverse direction and move to position X minus 2, then to position X plus 4, and so on in a zigzag pattern, each step moving twice as far from his initial starting position as before. As he has read during his study of algorithms for solving the lost cow problem, this approach guarantees that he will travel at worst 9 times the direct distance X minus Y between himself and Bessie before he finds her. This is also true, and the factor of 9 is actually the smallest such worst case guarantee any strategy can achieve. Farmer John is curious to verify this result. Given X and Y, please compute the total distance he will travel according to the zigzag search strategy above until he finds Bessie. The single line of input contains 2 distinct space-separated integers, x and y. Both are in range 0 to 1000. Print one line of output containing the distance Farmer John will travel to reach Bessie. And then the sample inputs are 3, 6, and the sample output is 9. To solve this problem, all we need to do is simulate exactly what it said. So, as we can see, in the base case, we have that Farmer John starts at position 3, and Bessie is at position 6. Well, the first part of the zigzag motion is that he moves to the right by 1 step. Well, we can see that his new position at 4 is still less than Bessie's position. So then he's going to have to return back to his original position, and then after that, he'll travel 2 to the left. Now, this value is still smaller than what Bessie's actual position is, so then he'll come back again to his original position. Now, he'll go to 7 because he moves 3. He moves 4. Well, now that we can see that Farmer John's position at 7 is greater than Bessie's position, that means as he was walking from 3 to 7, he must have encountered Bessie. Well, that is what we need to find. Since we know that his position is at least greater than or equal to Bessie's position, we'll have exactly how far he needs to move. And if we have an overflow, 7 minus 6, which is 1, we'll just need to account for that in our solution. Now, this is the case when Bessie is greater than Farmer John. Say we switched Bessie's position to be, let's say it was at position 1. Well, in this case, now we still got to simulate exactly how we did before. First, Farmer John goes 1 to the right. So we have it 1 over here. Now, he's going to go back to his original position. And then, he's going to move 2 to his left. Now that we can see that his position is the same as Bessie's position. So, again, we have the right solution. And that is the distance that he travels. If it was over, let's say he traveled 3 over, then this would still work because along his path from 3 to 0, he must have crossed 1. And since Bessie is at 1, we know that he's going to meet her at some point. Well, now we can just implement this pretty simply in Python. So the first step, of course, is just getting the input. And then we have it in X and Y. Then we have a couple of different variables. First one is turn. What turn tells you is either if we're going to the right of Farmer John's original position are to the left. Add by just basically means how much he's moving either to the right or the left. Current position is what he's at right now on the number line. Total is how much distance he moved. And then over is in case he overshot Bessie's position, we just need to account for that in our final solution so he doesn't go any extra distance. Well, first we just have a simple case. If they're both at the same exact position, we just want the total to be 0, and then we'll just simply print that out because add by will be 0 and over will also be 0. Well, now if we have Farmer John is less than Bessie, what we'll have is that while his current position is less than Bessie, first I'll do turn plus equals 1. This means for the first case, he'll be moving to the right. This total is add by times 2. The reason we do times 2 is because we can see that in this case, first he has to move over here, right? And if he does not meet Bessie at any of those points, then he has to move back to his original spot, which would mean it's 2 times whatever he moved by. So then we have total plus equals add by times 2. Now we have this case if add by equals 0. That's because we set add by equal to 0 initially. And if we never accounted for this, then if we multiplied add by 2, we would always just get add by to be 0. And we don't want that to happen because then we can never actually simulate our entire process. Once we do that, now we just do check this statement. If turn and then modulo 2 equals 1. Well, what this is saying is when we have Farmer John is less than Bessie, well, we'll know that the only time he can ever be at Bessie or greater is when he's moving to the right of his original position. And that's what turn is telling you. When turn is an odd number, it means that he's moving to the right. When it's an even number, he's moving to the left. So if we do turn modulo 2 equals 1, then we know that current position has to be added by because it is a possibility that he might meet Bessie. If he's going to the left, well, we always know that he can never meet Bessie. So then we don't really need to check that. And this case, even if we do minus equals x, we'll always know that current position is less than Bessie. So it's just simply not necessary. Then once current position is greater than y, then we just have this over. So this is just saying that if current position is greater than y, then we just want to keep this and we want to make sure how much ever he traveled extra is just stored, right? And then we'll subtract that from the total. And so say if current position he's at is 8, but Bessie's at 7, well, we know he traveled 1 extra. And we can see that over here. Total minus over. But the reason we have plus add by is because in case that he traveled this, curve pose plus equals add by, and this makes curve pose greater than y, greater or equal to y, then we want to go back and add by. If we don't, then we'll be missing the point at which he goes from his original position to the actual position, or greater than the actual position. Now, it's the same thing with when Farmer John is greater than Bessie. It's just slightly opposite. The only difference is now, instead of adding curve pose, we'll be subtracting it because we're going to the left. And also, instead of turn being odd, it should be even because remember, when turn is even, we're moving to the left. And then finally, we also know that if curve pose overshoots Bessie, we know that Bessie will be at a greater position than Farmer John. That's why instead of being curve pose minus y, it'll be y minus curve pose. And then again, we're just doing print plus add by minus over. And then, yeah, we could see that it works and that we get it for all the cases.